Hello, welcome to the course SJPHY1B01 Mechanics 1. The contents of this course is taken from An Introduction to Mechanics by Kleppner and Kolenko. Today we will start Module 2, which is Chapter 4, Work and Energy. I hope you all are familiar with the fundamental problem which we have been trying to tackle in the previous chapter. So we have a classical mechanical system. This could be a single particle, a collection of particles, or an extended body. We know all the interactions of the system, meaning all the forces acting on the system we know, and our aim is to predict the motion of the system at a given time. What is the position of the system? This is our aim. Okay. So if you are following the Newtonian mechanism, which we have mastered in the previous module, you apply the equation of motion. F is equal to ma, where a is the acceleration. Now, if you know the force acting on the system F, then mass is something which is measurable. So F and m, you know, when you do F by m, you get acceleration A. When you integrate acceleration with respect to time, you get velocity. When you integrate velocity with respect to time, once again, you get the position. So you get position as a function of the time. That's how you solve the system, right? Now, when you look at the equation of motion, F equal to ma, or F equal to m into dv by dt. So look at the left-hand side, and this is a function of time, right? Now, if you want to calculate velocity, you integrate it with respect to time once. And if you want to get position r and velocity v are related by v equal to dr by dt. So when you integrate velocity, you get the position r. So this is a simple integration with respect to time twice, right? So when you're doing integration with respect to time, on the left hand side, you are expected to do the similar integration on the right hand side. So we want the force to be a function of time. Then this is a straightforward mathematical procedure. But fortunately or unfortunately, force is usually a function of position. This is not a function of time. Because physicists in general are interested in interaction between systems. I suppose you have two systems, system 1 in location 1, system 2 in location 2. You want to know what is the force exerted by system 1 on system 2 or system 2 on system 1. Also, you want to know, as you move away from the system, how does the force vary. So basically, you are looking at a force as a function of position, not as a function of time. And how do I solve the equation of motion? That's a question. So for the sake of simplicity, let's first start with the one-dimensional motion, a particle or a system moving only in one direction. For example, a spring mass system oscillating in the x direction. Okay. So once you know how to solve the one-dimensional motion, we can quickly extrapolate it to the more general case of three-dimensional motion. So let me write down the equation of motion in one dimension. F is equal to ma, or in terms of position x, I can write f of x equal to m into d square x by dt square. Or in terms of velocity, same equation I can read it as m into dv by dt equal to f of x. So as I said, the left hand side is a function of time, right hand side is a function of position. So for uniformity, let's start with integrating both sides with respect to x. So let me assume that the system has moved from an initial position xa to a final position xb. Okay, so your integration limits are set now. So m integral dv by dt dx equal to integral f of x dx. Now solving the right hand side is straightforward because f is a function of x. You can directly integrate the right hand side. Now left hand side, I have an issue, right? Now the trick in solving the left hand side is integration with respect to x. Now you need to change into integration with respect to time t. And how do you do that? we can write dx equal to dx by dt into dt, right? Dt cancel, you have dx on either side. Dx by dt equal to v dt. So your integrating variable dx, now you change into in terms of dt. So the left hand side now becomes m into integral xa to xb dv by dt into dx equal to m into integral dv by dt v dt. Now since we are performing integration with respect to time, the limits of integral change. So previously I had xa and xb, now I have ta and tb, where xa is position at time ta and xb is position at time tb. Okay. Now you can solve this. This is straightforward. You can write dv by dt into v as d by dt of half v square. Because derivative of half square is going to be half into 2v into dv by dt. 2 and half cancel, so you have dv by dt into v. So the right hand side I am going to write as m into integral ta to tb d by dt of half v square dt. And what's the integration of d by dt of half v square? This is the term itself, right? Half v square. So when you multiply with that with m, you get half mv square. Apply the limits from ta to tb. So let me say velocity at time ta equal to va and velocity at time tb equal to vb. Then the result is going to be half m vb square minus half m va square. So let's substitute everything back into our original equation now. So my equation of motion now becomes half mvv square minus half mva square equal to integral xa to xb f of x dx. But if I want to take a more general case, suppose the system is originally at position xa and after time t it has moved to a general location x where the velocity is v. Now the equation gets modified as half mv square minus half mva square equal to integral xa to x f of x dx. So this is how you solve the one-dimensional equation of motion by integrating with respect to the position. Now once you get to this kind of an equation, you can quickly calculate what is the value of velocity v by rearranging the term and also performing this straightforward integration. And v is nothing but dx by dt. So when you do this, you get dx by dt. When you integrate that once more with respect to time, you get x of t. Okay, so this is how you solve the motion of a one-dimensional system. Let's do a couple of examples so that this procedure becomes more familiar to you. First, let's take a simple case of a mass thrown upward in a uniform gravitational field. So you have a mass m thrown vertically upward with initial velocity v0. You are asked to find out what is the maximum height, assuming the gravitational force to be constant and neglecting the air friction. So we know that a gravitational force is a function of height. So we can neglect that to make our analysis simpler. Also, the air friction is also neglected. So let's say the upward direction is a z direction. So this is motion along the z axis. And what is the only force acting on the system? It is the weight which always acts in the downward direction. So I can write F is equal to minus mg. Now let me suppose that the initial position is z0 and the maximum height, that position is z1 and the corresponding velocities are v0 and v1. So when you substitute the parameter into the previous equation, you get half mv1 square minus half mv0 square equal to integral z0 to z1 f dz. Substitute for f, you get minus mg integral z0 to z1 dz. Integral of dz is z. Apply the limits, so the right hand side becomes minus mg z1 minus z0. Now if you want to calculate the exact value of the height, you need to use some boundary condition or initial condition. So you are throwing a mass with initial velocity v naught. As it moves upward, the velocity keeps decreasing. Finally, when it reaches the maximum height, velocity becomes 0. Then it starts moving in the opposite direction, downward direction, and the velocity once again keeps increasing. Okay. So I can say at the peak, the velocity is 0, so v1 equal to 0. So I can put this condition into my equation now. So in this equation, half mv1 square, this term vanishes. So I have minus half mv0 square equal to minus mgz1 minus z0. You can cancel the negative side on either side. So you have half mv0 square equal to mgz1 minus z0. From this, when you rearrange terms, you get the maximum height z1 equal to z0 plus v0 square divided by 2g. Let's do one more problem which is a bit more involved. Let's take our classical case, or the classic case of simple harmonic oscillation. So you have a spring mass system with mass m attached to a weightless spring, and when you pull the mass to the right direction and release it, what happens? The mass is going to oscillate about the equilibrium position. Okay. So if you choose this as the equilibrium position, the displacement with respect to equilibrium position, you call it as x, and you will find that during the oscillation there is a restoring force acting on the system, and the restoring force is proportional to the displacement from the equilibrium position, and also the restoring force is always directed against the displacement. So if you move the mass to the right, then the restoring force will try to bring it back to the left. And if you push it to the left, then the restoring force will try to bring it to the right. So the restoring force F is equal to minus kx. Okay. Now let me assume that originally it is at the equilibrium position, denote that as x0, then you are going to displace it to a new position x, and the velocities are at equilibrium position, velocity is v0, and at position x, velocity is v. So plug all parameters into our standard equation. So we have half mv square minus half mv0 square equal to integral x0 to xf dx. Substitute for f, you get minus k into integral x0 to xx ds. Integral of x is half x square, and when you apply the limits, the right hand side become minus half kx square plus half kx0 square. Once again, we need some initial conditions. So remember, we have a second order differential equation, f is equal to ma, or f equal to md square x by dt square. And how do you solve a second order differential equation? You need to integrate it twice. So the thumb rule is that if you have an nth order differential equation, you need to have n initial conditions to find out the exact solution. So we need to have two initial conditions. So let's say at time equal to 0, initially the system is at rest. Okay. So I can say at time t equal to 0, initial velocity v0 equal to 0. I also know that when time equal to 0, the body is at the equilibrium position x0. So I can say at time t equal to 0, x equal to x0. So now let's put this information back into our equation. So I have minus half mv0 square on the left hand side. Since v0 equal to 0, this term gets cancelled, and I have half mv square equal to minus half kx square plus half kx0 square, or v square equal to minus k by m x square plus k by m x0 square. From this I can calculate v as square root of k by m into square root of x0 square minus x square. Okay, so basically this square root of k by m is a common term, I take it outside. Now velocity is dx by dt. Now from this I can calculate x by integrating it, right? But one thing you have to remember, on the left hand side you have both x and t terms, on the right hand side you have only x terms. So you need to follow a procedure known as separation of variables. So basically you bring all similar variables together. So I'm going to club all the x terms on the left hand side and all other terms I take it to the right hand side. So when you rearrange, you get dx divided by square root of x naught square minus x square equal to square root of k by m into dt. So you have all the x terms on this side, so you can integrate it with respect to x. Then you have all the time terms on the right hand side, square root of k by m. This is a constant, so it doesn't take part in the integration or differentiation, so you don't have to bother about that. So you can straight away do integration with respect to time on the right hand side. So what are the limits of the integral? Initially it is at position x naught, and after some time t it moves to position x. So integral limits are x naught and x here, and here initially time equal to 0, and after time t what's the position? That is our question. So the limits are here 0 and t. Now first let's do the right hand side, because this is simple. Integral of dt is t. Apply the limits, you get square root of k by m into t. In one of the previous classes, I said that the square root of k by m is a constant of motion known as the angular frequency omega. So the right hand side becomes omega t. And what about the left hand side? This is a standard integration result. This is there in your Clerk's table. You can refer to that. You are allowed to carry Clerk's table in the exam hall as well. So integral dx divided by square root of x naught square minus x square is arc sine x by x naught. Maybe you are not familiar with this term arc sine. Arc sine is nothing but sine inverse. Since our prescribed textbook follows this notation, I am going to use the term arc sine. If you want, you can write sine inverse in your notebook. Doesn't matter. So this is sine inverse x by x naught. Apply the limits x naught to x. Okay, so when you expand the left hand side, you get arc sine. First apply the upper limit x by x naught minus, when you apply the lower limit, you have arc sine x naught by x naught, which is arc sine 1. On the right hand side, you have omega t. Let's simplify this further. What is arc sine 1? Arc sine 1 is pi by 2. If you want, you can cross check this. Basically, apply sine on either side. So you have sine inverse 1 equal to sine pi by 2. Sine and sine inverse cancel. You have 1 equal to sine pi by 2. Right? Sine 1 equal to 1. So arc sine 1 equal to pi by 2. So when you put this result back into the equation, you get arc sine x by x naught equal to omega t plus pi by 2. Take sine on either side. So sine and arc sine cancel on the left hand side. You have x by x naught here. On the right hand side, you have sine omega t plus pi by 2. Or x equal to x naught into sine omega t plus pi by 2. And sine omega t plus pi by 2 is nothing but cos omega t. So you have x equal to x naught cos omega t. So you have solved the equation of motion of simple harmonic oscillators. As you can see, this is a sinusoidal function, right? So when you plot this function, you get a graph like this. So assume that originally you pull your mass to the extreme down position and release it. So cos 0 equal to 1. So originally you start from the equilibrium position. So time t equal to 0, cos 0 equal to 1. So x equal to x. That is your starting position. Then it moves downwards. So what happens? The displacement increases and it reaches the maximum point, and from the maximum point it starts decreasing. It comes to the equilibrium position, then it moves in the opposite direction. The displacement increases. Once again, the restoring force tries to bring it back to the equilibrium position. So displacement decreases, it goes to the equilibrium position. So always the restoring force try to bring your system towards the equilibrium position. So you have a sinusoidal movement. Now the same case, if the conditions are slightly different, you may get solution as x equal to some constant into sine omega t. omega t. So basically sine and cosine both are sinusoidal functions, and typically the most general solution is x equal to a sine omega t plus b cos omega t. Okay. Now let's quickly cross check whether our solution is correct. We know that at time t equal to 0, my velocity is 0 and position is x naught. Let's see whether that holds true with respect to this result. So when you say at time t equal to 0, x equal to x naught cos 0, which is x naught. And what about velocity? Velocity is dx by dt, which is x naught omega sine omega t. So when you put t equal to 0, you have x naught omega sine 0, which is 0. So both the initial conditions are satisfied. So this is the true solution. Okay. Now, what is the advantage of solving the equation of motion by integrating with respect to position? In the next class, you will see that using this procedure, we are going to derive an important theorem known as work energy theorem, and the generalization of work energy theorem results in one of the most fundamental, one of the most universal principles in physics known as conservation of energy. So stay tuned for that. Thank you.